Every CPU core and thread explained in detail sounds simple at first, but what if I told you that inside your computer there is a hidden world working at billions of operations per second, a silent orchestra of logic that never sleeps, never rests, and decides how fast your games run, how smooth your videos feel, and how responsive your system truly is? Welcome to the mysterious inner life of the CPU, the central processing unit, often called the brain of every modern computer, but in reality closer to an entire digital nervous system compressed into a piece of silicon smaller than your hand. And today, we are going to explore every CPU core and every thread in a way you have probably never seen before. Slowly, clearly, and deeply. So, imagine for a moment that your CPU is not a chip, but a city, a massive digital city where millions of instructions move constantly through invisible streets, never colliding, never stopping, always flowing. In this city, a CPU core is like an independent worker, a fully capable processor that can think, calculate, and execute tasks on its own. Early CPUs had only one core, just one worker trying to do everything at once, opening programs, running calculations, handling background processes, and keeping the system alive, which is exactly why older computers felt slow, unresponsive, and easily overwhelmed. But as software grew more complex, engineers reached a limit. Making one worker faster forever was no longer efficient, so they made a revolutionary decision. Instead of relying on a single core, they added more. This is how multi-core CPUs were born. Dual-core, quad-core, 6-core, 8-core, and now CPUs with 16, 24, or even more cores, each one being its own mini CPU, capable of fetching instructions, decoding them, executing operations, and writing results back to memory independently of the others. When you see a CPU advertised as having 8 cores, it literally means 8 separate processing units living inside a single chip, all working in parallel. But here is where the mystery deepens, because cores alone do not tell the full story. This is where threads enter the scene. A thread is not a physical object. It is a logical path of execution, a stream of instructions waiting to be processed. Traditionally, one core could handle only one thread at a time, one task flowing through one worker, but modern CPUs introduced a clever illusion known as simultaneous multithreading, or SMT, called hyperthreading on Intel CPUs. This technology allows a single core to handle 2 threads at the same time, not by duplicating the core, but by using its internal resources more efficiently. Inside every core exist multiple execution units. Some handle math, some handle memory operations, some handle branching logic, and in real workloads, many of these units sit idle while waiting for data. A second thread can step in and use those idle resources, keeping the core busy and increasing overall efficiency. This is why an 8-core, 16-thread CPU exists. 8 physical cores, each capable of running 2 instruction streams simultaneously. But here is where the mystery deepens, because cores alone do not tell the full story. This is where caches enter the scene. Each core has its own L1 and L2 cache, extremely fast but small memory areas storing frequently used data, and all cores usually share a larger L3 cache, acting as a central meeting point, reducing the need to access much slower system RAM. Threads benefit greatly from efficient cache usage because cache misses cause delays that no amount of extra cores can fully hide. This is also why CPU architecture matters just as much as raw core count. Modern CPUs use advanced prediction techniques, speculative execution, and intelligent prefetching to guess what data will be needed next, preparing it in advance. When these predictions are correct, everything feels instant. When they fail, performance briefly dips, revealing just how complex and delicate this system truly is. Operating systems act as the invisible conductors of this orchestra, deciding which threads run on which cores, when to pause them, and when to resume them. This process is called scheduling, and modern schedulers are incredibly sophisticated, especially with hybrid CPU designs that combine performance cores and efficiency cores. Heavy workloads are sent to powerful cores, while background tasks quietly run on efficient ones, saving power and reducing heat. CPUs constantly adjust frequency and voltage in real time, boosting clocks when only a few cores are active and lowering them when many cores are under load, which is why cooling and power delivery have such an impact on real-world performance. This is why understanding CPU cores and threads matters so much when choosing a processor. The best CPU is not defined by the biggest numbers on a box, but by how well it fits the way you actually use your computer. And now that you understand what is really happening inside your CPU, every benchmark, every spec sheet, and every upgrade choice will suddenly feel clearer and more meaningful. And if this video helped you see your computer differently, if it turned complex ideas into something simple and useful, you already know what to do. A like lets this video reach more curious minds, and subscribing means you won't miss what we uncover next, because this hidden world inside your machine is far bigger than what we explored today.